Hello dear students, all of you welcome to Vidyan classes. Today we will discuss some important short questions on symmetric and skew symmetry matrices. Elements of mathematics, exercise 4b, page number 115. State which of the following, question number 1, state which of the following matrices are symmetric, skew symmetric, both or not either. Let capital A be the given matrix. Here A12 is equal to A21, which is equal to 1. A12 means element of first row, second column is 1. A21 means element of second row, first column. Implies this A is equal to A transpose. Therefore, I represent A is equal to A transpose. A represent or I represent the symmetric matrix. Since A is equal to A transpose, the given matrix is the symmetry matrix. Second bit, let capital B is equal to, let capital B is the given matrix. Let capital B be the given matrix, where x, y, z order pair is not equal to 0, 0, 0 order pair. Implies this x not equal to 0, y not equal to 0, z not equal to 0. By the definition, since the diagonal elements are not 0, B is not skew symmetric matrix. In a skew symmetry matrix, all elements in the diagonal are 0. Since x not equal to 0, y not equal to 0, z not equal to 0, B is not skew symmetry. Again, A ij is not equal to A ji. Aij is not equal to Aji. For Ij is equal to 1, 2, 3. I varies from 1 to 3, j varies from 1 to 3. Aij not equal to Aji. For I not equal to j. Implies this the given matrix, that is B, is not symmetric. A12 is 1, A21 is minus 1, A13 is 2, A31 is equal to minus 2. B is not symmetric. Therefore, second bit implies neither symmetric nor skew symmetric. So it implies, second bit implies not either. Not either. That means B is neither symmetric nor skew symmetric. So second bit implies not either. Third bit, let capital C be the matrix. Let capital C represent the given matrix. Here Aij is equal to Aji. For Ij varies from 1 to 3, I not equal to j. A12 is 0, A21 is also 0, A13 is 3, A31 is 3, A23 is 2, A32 is also 2. Implies C is equal to C transpose. It is the definition of symmetry matrix. Therefore, the third bit implies symmetric matrix. C is equal to C transpose. Therefore, the third bit is a symmetry matrix. Fourth bit, let the given matrix be D. Here Aij is equal to negative of Aji. For Ij varies from 1 to 3. Also, Aij is equal to 0 for I is equal to j. That means the diagonal elements all are 0 for I is equal to j. Here I is not equal to j. The diagonal elements all are 0. Aij is negative of Aji. That means A12 is negative of A21. A13 is the negative of A31. It is the definition of skew symmetry matrix. Implies D is equal to negative of D dash. Therefore, the fourth bit implies skew symmetry matrix. Here D is equal to minus of D dash. It is the definition of skew symmetric matrix. Fifth bit, all elements in the given matrix are 0, so it is the 0 matrix. 0 matrix, which implies as 0 matrix is equal to transpose of 0. 0 matrix is equal to 0 matrix. 0 equal to transpose of 0 matrix. Also, zero matrix is equal to negative of 0 transpose. 0 is equal to 0, 0 dash, 0 means 0 matrix. These two conditions imply this. It is the definition of symmetric, it is the definition of skew symmetry. That means 0 matrix is both symmetric and skew symmetric. Fifth bit implies this, both means symmetric and skew symmetric. Note, 0 matrix represent both symmetric zero matrix, which is square, which is square. Zero matrix may be any order, but a square zero matrix is represent both symmetric and skew symmetric. Clear? Okay. Next, let E be the given matrix. All elements in the diagonal are not 0. So it is not skew symmetric. Since all elements in the diagonal, that means left up to right bottom, are not 0, implies this E is not skew symmetric. Since all elements in the diagonal are not 0. A12 is not equal to Aij. Aij is not equal to 0. Or I is equal to j. That means the diagonal elements are not 0, so E is not skew symmetric, and Aij is not equal to Aji. I varies, I and J varies 1, 2, 3. That means E is not equal to E transpose. Therefore, E is not skew symmetric, also not symmetric. E is not skew symmetric and not symmetric. Either. Clear? Therefore, the 58 implies not either. Clear? Aij not equal to 0 for I equal to j. That means all diagonal elements are not 0. So it is not symmetric. Is not skew symmetric. Aij is not equal to Aji for I equal to I varies 1 to 3. I not equal to j. Clear? So it is represent not either. Not either. Last bit, let F be the given matrix. Here Aij is equal to Aji. A12 is 0, A21 is 0. Negative of this. Negative of Aji. A13 is 1, A31 is minus 1. Ij varies 1 to 3. I not equal to j. Implies F is it is the definition of implies F is equal to negative of F transpose, which implies F is skew symmetric. Here Aij is equal to 0 for I is equal to j. These two conditions satisfy F is skew symmetric. It is symmetric or not? It is only A12, A13 is not equal to F is not equal to F transpose. Implies F is not symmetric, is not symmetric. Since A13, that is 1, is not equal to A31. A13 is 1, A31 is minus 1. F is not equal to F transpose, that means F is not symmetric, but it is F only skew symmetry. Therefore, B double I implies S is symmetric, skew symmetry. Clear? Once again, here A12 is equal to A21. That means A is equal to S transpose. Represent the symmetric matrix. It is the definition of a symmetric matrix. Second bit, all diagonal elements are not all 0. B is not skew symmetry. In skew symmetry matrix, all diagonal elements are 0. Here x not equal to 0, y not equal to 0, z not equal to 0. So, B is not skew symmetry. Again, A12 is not equal to A21. Aij is not equal to Aji for ij varies 1 to 3. For I not equal to j, B is not symmetric. So, it is neither symmetric nor skew symmetry. So, it implies it's not either. Third bit, Aij is equal to Aji. That means A13 is the same as A31 for I not equal to j. Implies C is equal to C dash, that means C is a symmetric matrix. It is not skew symmetric, since in skew symmetric Aij is equal to, it is not skew symmetric since all diagonal elements are not 0. It is not C is equal to C. Since the diagonal elements are not 0, it is not skew symmetric. Therefore, the third bit is only symmetry matrix. Clear? Next, all diagonal elements are 0. Aij is negative for Aji, and Aij equal to 0 for I is equal to j. That means all diagonal elements are 0. And Aij is negative for Aji. It is the definition of skew symmetry. That implies the fourth bit is skew symmetry. It is not symmetric since A12 is not equal to A21. Here, the square matrix is a 0 matrix. Here, the given square matrix is a 0 matrix since all elements are 0. 0 matrix implies 0 is equal to 0 transpose, and 0 matrix is equal to negative of O dash means that is the transpose of 0 matrix. Both satisfies. So, it is both symmetry and skew symmetry. Note 0 matrix which is the square represent both symmetry and skew symmetry. Sixth bit, all diagonal elements are not 0, so it is not skew symmetry. is not skew symmetry. A12 is negative. Also Aij is not equal to Aji. I varies 1, 2, 3. I not equal to j is not equal to E dash. So the sixth bit is neither symmetry and skew symmetry. Clear? So it implies not either. The last bit, here Aij is negative of Aji. That means A13 is equal to minus of A31. Aij is negative of Aji. I and j varies 1, 2, 3. Also it is satisfied Aij is equal to 0 for I equal to j. So it is f is a skew symmetric. A13 is not equal to A31. That means f is not equal to f transpose. F is not symmetry. Therefore, VII is skew symmetry. It satisfies only the definition of skew symmetric. Clear? Are you clear? Okay. Note down. Question number 2. Prove that if A is symmetric matrix, then A to the power n belongs to capital N, is a symmetric matrix. A to the n belongs to capital N. Capital N represents the set of natural numbers. We have to prove A to the n is symmetric. Since n belongs to capital N, the statement can be proved by the method of induction. Prove. The statement can be proved using the principle of mathematical induction. Let Pn be the given statement. Pn so that A to the power n belongs to capital N, is a symmetric matrix. If capital A is a symmetric matrix, then A to the n belongs to capital N is a symmetric matrix. Step 1. In mathematical induction, there exist 3 steps. The first step must be proved. The second step will be assumed that the statement is true. The third step will be proved using the second step. Step 1 for n is equal to where n a to the n belongs to is a symmetric matrix where capital A is a symmetric matrix. Step 1 n is equal to 1. P1 so that a to the power 1 is equal to a, given a is a symmetric, is a symmetric matrix. So P1 is true. The first step must be proved. So P1 is true. Second step, step 2. For n is equal to k, let Pk is true. For some positive integer k. Let Pk is true for some positive integer k. Pk so that a to the power k is a symmetric matrix. The second step will be assumed that Pk is true. That means a to the k is a symmetric matrix is true. A to the k is a symmetric matrix is true. To show step 3, step 3 for n is equal to k plus 1. To show p k plus 1 is true whenever Pk is true. Using the second step, we will prove the third step. Now, Pk plus 1 so that Pk plus 1 a to the k is a symmetric matrix. That implies a to the k whole dash is equal to a to the k. Since it is the definition of symmetric matrix, a to the k is a symmetric matrix. Transpose of a to the k is equal to a to the k. Now, we will prove Pk plus 1 is true whenever Pk is true. Now Pk plus 1 which is same as a to the power k plus 1. Now to show a to the k plus 1 is a symmetric matrix. A to the k plus 1 whole dash is equal to a to the power k into a whole dash, which is same as a dash a to the k dash. since transpose of product of the matrices is equal to product of the matrices in the reverse order, since it is true. A to the power A transpose is equal to A. A transpose is equal to A. A transpose is equal to A since A is symmetric. As A is symmetric. Clear? A transpose of A to the K. Transpose of A to the K is equal to A to the K since A to the K is a symmetric matrix. Which is same as A to the power K plus 1. Transpose of A to the K plus 1 is equal to A to the power K plus 1 implies this. A to the power K plus 1 is a symmetric matrix. By the given hypothesis, transpose of A to the K is equal to A to the K. So A to the K full dash is equal to A to the K since A to the K is a symmetric matrix. Transpose of A to the K plus 1 is equal to A to the K plus 1. So A to the K plus 1 is a symmetric matrix. Implies as P K plus 1. We have to prove P K plus 1 is a symmetric matrix. Implies as P K plus 1 is true whenever Pk is true. Therefore, Pn is true for all n belongs to capital N. Clear? In mathematical induction, the first step must be proved for n is equal to 1. A to the power 1 is equal to A is a symmetric matrix since it is given A is a symmetric matrix. So P1 is true. The second step must be assumed that the second step is assumed that Pk is true. For n is equal to k, Pk is true for some positive integer k. Pk such that A to the k is a symmetric matrix. By the definition, transpose of A to the k is equal to A to the k. Step 3, for n is equal to k plus 1. To show Pk plus 1 is true whenever Pk is true. Now Pk plus 1 is equal to A to the k plus 1. We have to show that A to the power k plus 1 is symmetric. By the definition, transpose of A to the k plus 1 which is same as A to the k plus 1 is same as A to the k into a whole transpose which is same as A transpose and transpose of A to the k since transpose of xy is equal to y transpose into x transpose. A to the power A transpose is equal to A since A is symmetric. Transpose of A to the k is equal to A to the k by the given hypothesis. It is the given hypothesis. A into A to the k which is same as A to the k plus 1. Implies transpose of a to the k plus 1 is equal to a to the k plus 1 implies yes, a to the k plus 1 is a symmetric matrix. Is a symmetric matrix. Therefore, Pn is true for all n belongs to capital N. Note a to the n is a symmetric matrix if A is symmetric. A to the n is symmetric matrix if A is symmetric. For n belongs to capital N. Implies A square A cube n is equal to A square is a symmetric matrix, A cube is a symmetric matrix, A to the 4 is a symmetric matrix, A to the 5 is a symmetric matrix as n is n belongs to capital N. A to the n are all symmetric matrices. A to the n is a symmetric matrix if A is symmetric matrix, which is proved in question number 2. As n is a natural number, for n is equal to 2, A square is a symmetric matrix, n is equal to 3, A cube is a symmetric matrix, n is equal to 4, A to the 4 is a symmetric matrix. Similarly, A to the n are all symmetric matrices since n belongs to capital N. Clear? No doubt? Question number 3. So that the matrix B dash A B is symmetric or skew symmetric according as A is symmetric or skew symmetric. We have to prove B dash A B is symmetric or skew symmetric according as A is symmetric or skew symmetric. Let S1, let AG symmetric, which implies A is equal to A transpose. We have to prove B dash A B is symmetric or skew symmetric. B dash A B whole dash is same as B dash A dash B transpose A transpose transpose of B transpose. Since transpose product of the matrices is equal to product of the transposes taken in the reverse order. So this is same as this, which is same as B transpose A transpose into B. Since transpose of B transpose is equal to B, which implies this. Transpose of B transpose A transpose B is equal to B transpose A B. Therefore, it is satisfies the definition of a symmetric. Implies this. Therefore, B dash A B is a symmetric matrix. A is a symmetric matrix. B dash A B is a symmetric matrix. Since it is satisfied this condition, it is the definition of symmetric matrix. Case 2. A is symmetric or skew symmetric. Let A is a skew symmetric matrix. By the definition, A transpose is equal to minus A, or A is equal to minus A transpose. Now, transpose of B transpose A into B, which is same as B transpose A transpose of B transpose, which implies a B transpose A transpose is equal to minus A. This is same as this according to this rule. A transpose is equal to minus A. B double dash is equal to B, which is same as minus of B dash A B. Since alpha A B is the same as alpha A B, which is same as A alpha B. That means matrix product is associative with respect to scalar. Here -1 is the scalar, which is taken outside, which implies this. B dash A B whole dash is equal to B dash minus B dash A B. It is satisfies the definition of skew symmetric. Implies this. It is satisfies the definition of a skew symmetric. Therefore, B dash A B is a skew symmetric matrix. When A is symmetric, B dash A B is the symmetric matrix. When A is the skew symmetric matrix, B dash A and B is a skew symmetric matrix. A is the symmetric, B dash A B is the symmetric. A is the skew symmetric, B dash A B is a skew symmetric. Clear? Next, question number 4. So that for any square matrix capital A transpose is a symmetric matrix. Very easy question. A is a square matrix. A is a square matrix of is a square matrix. Implies A S transpose is defined. Clear? Since A is a square matrix, A transpose is defined. We have to prove A transpose is a symmetric matrix. A dash whole dash which is same as A dash whole dash A dash. Since xy transpose of xy is equal to y transpose into x transpose, which is same as A dash. Since transpose of A transpose is equal to A, which implies A transpose whole transpose is equal to A transpose. Therefore, A into A transpose is a symmetric matrix. Since it is satisfied the definition of symmetric matrix, this implies A dash is a symmetric matrix. Clear? Clear? Okay. Write down.